Sorry for that brief interruption, but that is part 3, and we will figure out that right now mean squared of between divided by within gives us 11.07. If you take a look at the numbers, you can notice that the degrees of freedom add up to the total. Sums of squares add up to the total, which means that you can use them reverse and forward. You can do total minus within to get between, total minus between to get within. Those all work very well. So now that we have our f obtained right here, we need to do a critical lookup. In our book, it's going to be page 435. If you don't have a book, find an F table, and you need to know our degrees of freedom between, which from before was 21, and our degrees of freedom within, which will tell us the row, which was 2. We look this up, we end up with a critical value of 3.49. Now our F obtained is greater than our critical, so we would reject the null and find support for the alternative, stating that at least one of our means is different from the rest. Now remember, you can always draw this out if need be. Now we can see from here that the 3.49 creates the critical region. All the area to the right will cause us to reject it. The 11.07 falls in that region, so therefore we would reject it. Now that we know that we reject it, we can calculate an effect size as well as a post hoc. First thing we're going to focus on is the effect size. The effect size is pretty simple. It is very much like R squared, where it tells us the proportion of variance, so how much influence, how much of the movement in scores is attributed to the memorization type. So how much does memory actually influence? What percent of how many words you recall can we say is due to your strategy type? To get this, we use eta squared. Looks like an n with a square, and it's a simple formula. Sums of squared between, which we know is 65.33, divided by sums of squared total. That's going to give us 0.51, which we can see from our slide is going to be a large effect size. Next we're going to do post hoc comparisons. The reason why we run a post hoc comparison in an ANOVA is because it tells us at least one is different, but it doesn't tell us which one is different. And especially if we have 3 or more groups, it could be any of them. Think about it like this. If you walk into a room and there's only 2 people and they say there's a difference of opinion, you know which 2 people have a difference of opinion. However, if there's 3 people, you don't know if all 3 people have differing opinions, or if just 2 and one have a different opinion. We don't know how it works. So in order to figure this out, we're going to run what's called a post hoc. For our class, we're mostly going to focus on Tukey's HSD, which is when you have equal ends. Fisher's protected T is something we can get through SPSS, but we're not going to learn how to do by hand. With Tukey's HSD, we need to get a new statistic, a new piece of information from something called a Q table. That is currently in your book on page 439, or as always, you can look up a Q table online. K is the column, is the number of groups, and then we use degrees of freedom within to determine which row that we're going to look at. Remember, it's just a basic table. Degrees of freedom within tells us how far down we go. The K for the column tells us how far across we go. And our book is going to have 0.05 and 0.01. We're going to use 0.05 as our alpha, as our default. In order to calculate what's called the HSD, which stands for the honest significance difference, this sets a border of which, if the value is greater than that, the HSD creates a border where If the differences between the two groups that we're comparing is greater than that HSD, we're going to say it's significant. Much like we've been doing previously. And again, you can always draw it out. Our honest significant difference is going to be the Q value we looked up times the mean squared within, which we get again from our table. It's going to be this value right here, 2.95, times n, which we know is 8. Because these have equal sample sizes, we know there's 8. So let's run through the math. Let's look down here. We have Q, which if we look it up, will be 3.58 times the 2.952. A little bit more precise than what we have in our table, but that's okay. Divided by the square root of 8, divided by 8, then we take the square root of that. So 2.952 divided by 8, which we then take the square root of, will be 0.607. I recommend doing that first before doing all the rest of the multiplication. When you're doing it through the calculator, it'll make your life simpler and make sure you're more precise. Then we've got 2.17. That is our cutoff, which means if there is any value greater than 2.17, now it can be positive or negative because you can do rote first in this case or imagery first. It doesn't matter. There's no rhyme or reason as to which we do first. So remember, for the honest significant difference, it comes down to absolute values. We have negative 1.5. That is not further away than 2.17. 4, negative 4 definitely is. Negative 2.5, that is. Oftentimes, it's good to use the larger number first. I gave an example of negatives just to kind of illustrate in case you make a mistake and do negatives, end up with negatives and be like, oh, well, it doesn't work. It still does. For those that are going to be doing it with SPSS, one column for the independent variable, one for the DV, just like when we do a t-test, an independent t-test. Gives us everything but effect size, and we'll do this together in class. Graphs the same as independent. APA style, F as degrees of freedom between, comma, degrees of freedom within, equals F obtained. We get our p-value. We have to calculate our eta square and Tukey's. But let's take a look at a full picture of what our results are. Now remember, with results, we really plug and play. And ANOVA, just like with t-test, is just a template. A between subjects ANOVA, which when we're going to be doing a new one called within or factorial, we can say any of those ANOVA was calculated with whatever our dependent variable is, and then our independent variable, and then we put our levels in there. The effect of, which is something that we're now going to be using. Strategy was significant, and we put our F, as we just did on the last slide, comma 221 equals 11.06, P equals 0.001, eta equals 0.51, and then we go for our post hoc. Again, we only use a post hoc, just like an effect size, if there is significance. Tukey's HSD post hoc analysis showed that participants who used the strategy scored significantly higher than those who used rote rehearsal and those who used imagery, because 8 was greater than that 2.17, so 8 minus 4 was greater than that 2.17. Same thing with 8 minus 5.5. That was also. However, the difference between rote rehearsal and imagery was not greater than 2.17. For another example on how to calculate ANOVA by hand, please check my YouTube channel. Thank you for watching all 3 parts, and I will see you all in class. And do not forget to fill out and answer the reading quiz.